Thank you. Good morning and welcome to third Open Networking Summit. I'm Guru Parulkar. I serve as the chair of Open Networking Summit. Please meet Sadef Uzkana. She is in charge of all the logistics and operations of Open Networking Summit. So if you like your experience, at Open Networking Summit, you know whom to thank. Okay? We are very pleased with growing momentum, growing excitement for software-defined networking as well as for Open Networking Summit. I want to take a minute to tell you about Open Networking Summit. We would like you to think of Open Networking Summit as your premier SDN event of the year. We exist to help SDN become more successful. We exist to serve the SDN community, and that is all of you. I want to tell you how we put Open Networking Summits together, what goes into it. So we always anchor our events around the leaders from all parts of the SDN ecosystem. That is researchers, inventors, innovators, business leaders, entrepreneurs, venture capitalists, and so on. With these leaders, we try to create the best content that we can. Bringing the highest quality program to you is our most important priority. And we don't let anything come in the way of creating the highest quality content. For example, as opposed to almost every other event, we don't let sponsorship influence the content of the program. And this is so unusual. Every time a person will call from a company saying, I want to sponsor and I want to have a speaking slot. And I have to repeatedly tell everyone that sponsorship and the program is completely separate. You can give us all the money and still may not get a slot, and you may give us no money, but if you have something important to tell our audience, we are always happy to have you. Okay? Of course, we are a non-profit organization. We depend on sponsorship, but we want to keep sponsorship and the program completely independent. Okay? Finally, it is important to create a quality experience from our participants, that is in terms of create the quality dialogue in a fun and exciting setting. And that's what we are trying to do. Hopefully we are succeeding. Our hope is that everything together helps us make SDN more successful and help grow the SDN community, and that is our mission. Okay? Now, as SDN is gaining momentum, as SDN is growing, so is ONS. So ONS is growing in terms of number of participants as well as in terms of its scope. So for example, this year we have added research track and a developer track. So research track, we want to bring the latest research results to this particular community, and more importantly, we want to encourage more interaction among or between academia and industry. We have also added developer track this year so that we can bring developers together around open source SDN projects or open source SDN tools and platforms. We have added hot startups and venture investing. We know in high tech, startups are the ones that lead with disruptive technologies and disruptive solutions. So we want to make sure that we highlight that and we bring those to you as a community. We also have added something called SDN Plugfest to allow all the vendors and solution providers to show how different pieces of SDN come together and together create a more complete solution. Finally, we have also added something called SDN Idol at ONS to create some kind of a fun, friendly competition among companies so they can showcase their latest and greatest products and solutions. Okay? So I hope you enjoy the broader scope and what we are trying to bring to you. Similarly, we have more than 40 exhibitors that are demonstrating their products and solutions at ONF this year. There are more than 10 demonstrations from academic and research institutions as well. And you can see that these exhibitors are coming from very different parts of the ecosystem. And I think it is fair to say that industry is kind of embracing SDN at this point. At the same time, you know that there is too much hype about SDN, and there is something called SDN washing. If you have not heard about this phrase, what that means is that companies are taking their existing SDN products and then positioning them as their existing products and positioning them as SDN products. Okay? So that is something we have to be careful of. As a chair of Open Networking Summit, I have done my part to keep SDN washing as much out of the ONS as I could, but there is only so much I could do. So I thought what I would do is that introduce you to the basics of SDN again before I introduce our keynote speaker, so that at least you know what SDN is about, at least how we define SDN. And so when you are looking at all the talks and so on, you are able to kind of keep them honest or evaluate these talks in that context. So the first thing that is most important about SDN is the separation of control and data plane. Lifting embedded control plane complexity that is in these proprietary boxes out of these boxes and putting them in software running on servers. And as a result, simplifying these forwarding elements and having them what you can call a well-defined forwarding abstraction. Then once you lift this control plane outside, we have an opportunity to re-architect the control plane. And you can re-architect it in terms of number of abstractions, number of layers of software with well-defined interfaces. And so the lowest, and then there is a vendor agnostic interface between the control plane and data plane that lets you program the forwarding abstraction or forwarding plane, and OpenFlow is an example of that protocol. There could be others, but those other protocols ought to have the following attributes, that is vendor agnostic, open, and be able to program the forwarding plane of the different types of forwarding elements. Okay? When you go to the control plane, the lowest level of the control plane, we call it controller or network operating system. And the job of the network operating system is to create and maintain what we call a network map. And so create this network map and offer it to the applications, control and management applications that are running on top of this particular network operating system. And the big idea is that if you can keep this network map at logically one place, then writing this control and management application become very, very easy. Because if you have it there, then you can manipulate that network map very easily, and you can leave rest of the details to the network operating system. And that is kind of the appeal of software defined networking. And then of course offer the interfaces there. Now if we do this right, then we can bring openness and programmability to the infrastructure to enable more innovation, that is very important, accelerate new revenue generating services with right abstractions, open API and configuration, and we can help reduce CapEx and OpEx by moving away from closed proprietary complex boxes and exploit abstractions to create revenue generating or whatever, the control and management apps to reduce the operational expenses. So that is my last thing to message to you, that as you listen to different presentations today and tomorrow at ONS, keep this SDN definition, the motivation for SDN in mind, and evaluate and challenge the presenters whether they are delivering on this promise or not. Okay, with that, I want to have an opportunity to introduce our keynote speaker, Vint Cerf. Okay, we have a problem. Vint is stuck in his office, so we are sending a special mission to fetch him. So let's see how it is progressing.
Mr. Bond. Mr. Cerf.
Oh, James. Hello. Are we ready to go?
Ready, sir.
Mr. President?
Mr. Cerf, sir. Mr. Bond, sir. Let's get this show on the road.
Okay.
Let's do it, boys.
Let's go.
Ladies and gentlemen, on behalf of Her Majesty's Government, I bring you a genius, a hero, and a man who brought us the internet, Vint Cerf.
Aren't you all tuckered out from all that? Well, this is a real pleasure. Thank you so much for letting me drop in this morning. I feel a little funny about this because we have this term software-defined networking, and in a funny way, it's always been about software. Even the original packet switches of the ARPANET were based on software. It's just that you're in the middle of a kind of renaissance in thinking about what networking can do, because there's more than we can get the software to do. There's more than we can get the hardware to do in cooperation with it. And so in a very interesting way, you have an opportunity to reinvent the whole notion of networking. And so I'm very excited about that. It's nice to see this kind of fresh, new thinking happening, in spite of the fact that the internet has been around in concept for 40 years and it's been in operation for 30. Here's an opportunity in the beginning of the 21st century to think differently and anew about what networking is all about. Can I get the next, where's the clicker? Oh, here it is. How many people does it take to run? There we go. So some of you will recall that there was a small error made in our estimation of the number of things on that would be needed on the net. I just thought it would be interesting for you to see what our thought process was. We had just completed doing the ARPANET. It was in operation in 1972, demonstrated to the public in October of that year. And we got to thinking, okay, if we're going to do this multi-network thing, how many networks will there be in each country? And we thought, well, building the ARPANET was not exactly cheap. So we thought, well, maybe there will be 2 per country because you want some competition. And then we said, how many countries are there? And there wasn't any Google to ask that. So we guessed 128 because that's a power of 2, and that's what programmers usually think in. So we figured 256 networks, and then the question was how many computers would there have to be on it? And we thought, well, let's be generous. The machines of the time were typically large-scale time-shared machines that served anywhere from 1,000 to 10,000 people. So we thought about 16 million of them. Okay, so that's another 24 bits. That's 32 bits of address space. And we even considered in 1977 whether we should expand that because the Ethernet had been built, and some people thought there would be a lot of them. Nonetheless, we stuck with the 32-bit number because most of the packets flying around in the ARPANET at the time were 1 byte long. It was echoplex operation. And 128 bits times 2 of addressing on a packet just seemed like, a red-faced overhead, so we didn't do that. And it lasted until February of 2011 when we basically ran out at ICANN. So now we have IPv6, which is beginning to finally filter into the system. I see Bob Hinden sitting right here in the audience. It's his fault. So if you don't like IPv6, you can go after him for that. If you have an opportunity to get it turned on, or if you have service from some ISP that hasn't turned it on, do us a favor, call and holler at them. Okay. Now, if you are off in the software-defined networking space, this is an undefined space. Just because it says software-defined networking doesn't mean that it's the same thing. That's like cloud, right? Everybody says, well, it's all these clouds, but they aren't all the same. And certainly you can invent an arbitrarily large number of different kinds of software-defined networks. The thing I want to impress upon you is that if you want things to interoperate, standards are really important. This isn't to say you shouldn't explore brand new ideas and things that might be incompatible, but as you get to the point where you want to have something big happen, spend some time working on getting agreement on standards. It creates an opportunity for competition because multiple parties can build things to that standard. That's certainly what happened in the case of the internet. And these standards also create a certain amount of stability. And stability is your friend in networking environments. If you can't rely on some stable point in the architecture, then you'll have a lot of trouble making things work reliably. And finally, whatever you do, you want to make sure that you design it so that it is adaptable and capable of change. We were very fortunate in the design of the internet to simplify things, to keep things layered in order to allow change to occur intra-layer, and of course change to occur across layers in some sense. For example, above the level of the internet protocol, we have multiple transport level protocols could be introduced and multiple kinds of underlying transport as well. So that's important. The second, branding turns out to be fairly important. If you're interested in this not as an academic exercise, but because you are interested in creating a product or a service that people are attracted to, then it turns out branding is really important. What is not so important necessarily is proprietary things. That's why the standards should be as open as possible. They should be freely accessible. That's not the thing that you want to control. The thing you want to control is the implementation of those standards. And so there are people who have built different pieces of equipment and different kinds of software that make the internet work. And what they have done for their success is to brand those so that people want to buy that brand instead of someone else's brand of the same protocol. So you brand the implementation and you brand the service, but please don't patent the protocols. Frankly, I think all of us have seen some real abuse of the patent system, especially in the software domain. And so if you're interested in software-defined networking, I think patenting may not be your friend. Another thing which is terribly important is how you treat the design of the system. In the internet world, we learned some important things about loose coupling. If you design a system that's very, very rigid, that has tightly controlled protocols and that have very little in the way of adaptability and flexibility, you get a potentially high performance system, but it may be very, very brittle. And one of the things that's helped us a lot, I think, in the growth of the internet, it's scaled by a factor of over 1 million since its implementation, is that it's a rather loosely coupled system. An example, if you look at the internet protocol spec, the IP spec, you discover no mention of routing. And the reason is that we thought that should be a separate activity that wasn't something that was in the domain of the implementation of the IP layer of protocol, but rather something else. And that allowed for quite a bit of experimentation with different kinds of routing protocols at a time when it was not certain what kind of routing would be needed. And so this kind of loose coupling, or how about the fact that you can run internet packets over any kind of underlying transmission system, again, a kind of loose coupling. So I think loose coupling here is an important concept to hang on to. The second thing is that if you standardize on what is actually transmitted, so the format of the objects and the handshaking, the protocols that are associated with them, if that's what you focus on, if that's the visible element, then nobody has to know what's going on in the software. Unlike an API style system where actually both ends of the either side of the interface have to know what the other is doing. So having formats and protocols and conventions that are visible sort of on the line or in the air or however things are being transmitted as the primary way of achieving compatibility is a really powerful tool and something I strongly recommend. Modularization and layering also turned out to be very helpful because they simplify things. They hide information that you don't need to know. So the endpoints of the internet didn't need to know anything about how the internet was structured, what its architecture or its topology was, how many different networks were involved, how many networks your packets were going through. All you had to say was send this to that destination. And so this hiding of detail has turned out to be very powerful. It doesn't have to be layers necessarily, but modularization, I think, is a clue. Now, open source is a big help here in many cases because it helps people get past the primary barrier of implementing things because they have something to start with. So it isn't necessary to pursue software-defined networking using open source as an avenue for that, but it has turned out to be a very enabling kind of thing. So I strongly recommend use of open source, especially for reference implementations of things that you would like to have widely used. Now, OpenFlow is really quite an interesting view of networking. It's a kind of a refreshing and open, it's an open idea, primarily because the notion of address is redefined, at least as I understand it. Historically, we would design networks that had packets that had addresses that said, please send it to that termination point. This is true of the telephone system, at least in the early days when you dialed a number. It literally meant, please send or make a connection to that wire over here. And in the internet world, please send this packet to that physical termination point of the network. But in OpenFlow, the inventors removed that constraint and said, why should we limit ourselves to just the bits that are in this thing we'll call an address when we could use any bits in the packet to decide where something should go? Now, those of you who, probably everyone in the room, who know what a routing table looks like or a forwarding table looks like or a forwarding information base looks like, you know that what happens is that you look at some bits in the packet and you look them up in the table and then you decide based on what's in the table where to send that packet. Well, there's nothing in that mechanism that limits you to using only the address bits in the packet. You could use any of the bits. In fact, you could ignore the address bits. And in some cases, that's exactly what people have done. Content-based routing is, in some sense, about taking some content from a packet and using it to decide what to do with that packet. Van Jacobson has been a very strong proponent of that kind of working. Multicast works just fine that way because it's not really a physical specific destination address. It's to anybody who said, I would like to hear information coming from a particular source. Another thing which has turned out to be a very important step in the OpenFlow design is the separation of control from the flow of data. And you know, I look back on this and think, boy, I wish we had done that in the internet design, but we didn't. What that does is reduce the attack surface against which people with abusive applications can attack, whether they're attacking a router or attacking a host or a server or a laptop or something else. Everything is, in some sense, visible, including the control system. This is sort of like the early days of the telephone network that was attacked using blue boxes because the control was in the same frequencies as the voice path. And they were soon very concerned about that and invented signaling system number 7 to move the control away from the voice path of the circuits that were used for telephony. So this, in a sense, is a revisiting of that kind of separation. It's a very powerful and very useful step. The other thing which is rather nice about the OpenFlow design is you can group flows together. Now, there was a variation on this. Those of you who know about MPLS will recall that the way things worked is you would take groups of packets or trains of packets and then associate them with particular paths in the underlying fiber network so as to sort of guide the traffic to different lambdas in an optical fiber network. Once again, you can do that. And the most important thing about OpenFlow, in my view, is that it can be made to look like the internet. So you don't have to start out with something that looks different. You can start out with something that looks the same, but it's implemented differently. And in some sense, the heart of an awful lot of innovation is to start out with something that does what everything else used to do and looks just the same to make it easy to introduce. Then you say, oh, by the way, now that we've implemented it this way, we have a collection of new things that we can do that you couldn't do before. Google is a big fan of OpenFlow, and Urs Holzle, who runs all of our infrastructure engineering, decided that we would implement internal networking in all of our data centers using OpenFlow. This has led to a significant increase in the utilization of the underlying transmission system in each of the data centers. And I was very impressed by two things. First of all, this ran at such high speed that we had to tweak the TCP in order to deal with flow control and stability and everything else. And these guys actually did the implementation in something like 6 to 9 months. To implement OpenFlow, put it into new hardware, to jack up the entire application level of the system and slide this new networking mechanism underneath in 6 to 9 months without taking anything down was absolutely incredible. Nobody noticed on the outside that we had a whole new networking capability inside each data center. So that's just an example of how robust this particular idea has turned out to be. There are a lot of different things that you can do with software-defined networking. One example that was explored by the Defense Advanced Research Projects Agency by Preston Marshall, who now works for Google, by the way, is to look at adaptation in wireless environments. Certainly one of the things that we've been interested in at Google is making use of the TV white spaces and trying to take advantage of available communication capacity where it otherwise would have been unused. That turned out to be quite a long debate over how you could do that without interfering with things like wireless microphones like the one I'm wearing right now. And the conclusion was to have a database that knew about at least static locations where these kinds of devices might be used and might experience interference. And using that database, the software system can figure out whether or not it's okay to radiate. Of course, sensing to see whether or not the spectrum that you're interested in is in use at the moment is also another mechanism for allowing that kind of adaptation. So the software is getting smarter and smarter about the environment that it's operating in and taking advantage of that knowledge in order to use capacity that would otherwise go unused. Some of you may have heard that if you take a radiometer, a broadband radiometer, and try to look at how much of the spectrum is actually being used at any one time, it seems to be about 2%. And so this says that dedication and allocation of capacity by frequency bands is a very inefficient way of using the radio spectrum, and using software-defined networking, we may be able to make much better use of it by cohabiting and allowing multiple systems to be using it in a shared way. Another possibility, of course, is that you're in a situation where you have a lot of dynamics, or maybe you're in the military environment where somebody's jamming the network, or you're in motion, you're in an urban environment, there's a lot of reflections, all kinds of things that could be compensated for by software mechanisms, or even combinations of software and hardware like MIMO being a way of dealing with reflected signals and adding up the energy in order to get a better signal-to-noise ratio. So these kinds of things are obvious extensions of software-defined networking. Another one is dynamic power management, something that the Qualcomm team made very heavy use of in its CDMA designs. And here we're trying to make sure that we don't radiate with more power than is absolutely necessary to communicate with the party that we have want to send our data to. Another thing which I found quite interesting is this notion of ignoring what we normally think of as an address as being a physical termination point in a network somewhere. There isn't any reason why the notion of the destination of a particular packet has to be a physical thing. It could be that we're trying to reach a process that's hiding somewhere in the network. And when Bob Kahn was designing something called the handle system, his idea was that digital objects should have unique and persistent identifiers, unlike domain names, which you all understand are not persistent. If you don't keep paying your rent, eventually the domain name might go to someone else, or it might simply stop being recognized. That's not stable. That means that if you use URLs to point to something, but the domain name is no longer available, then the object that you pointed to is no longer discoverable. In the handle system, the idea is to retain an identifier permanently and not ever to change it. It's always bound to the object that it was associated with. So the idea might be to use these digital object identifiers as the information in the packet that tells you how to route something. And it could very well be, of course, that you have to do an indirect lookup. You have this unique identifier, but it doesn't itself tell you where something is. So you may still have to do lookups, and hardware, again, can help, just as we do with the domain name system, in order to reach a particular destination. Our interest is not the pipe. Our interest is in the object that is on the other side, somewhere inside the operating system. Bob and I also spent some time back in the mid-1980s looking at the possibility of mobile software moving around in the network, performing tasks for you and then coming back and reporting the results. This is another kind of mobile software, and although we only experimented with it for a little while, in some sense, today we have something like this happening to us because we have JavaScript being downloaded into web pages and interpreted at the destination browser as a kind of mobile software that's doing things for us. So these ideas are all well within the ambit of the space that we think of as software-defined networking. Another thing that can be quite helpful is the ability not only to send traffic over multiple paths at the same time, but also to make use of alternative media at the same time. So if you have satellite capability and optical fiber and mobile radio capability, all of those things could be used in order to build a network. This is the inverse of doing what we did in the internet design, which was to isolate particular media to be an autonomous system. So we had mobile packet radio, we had packet satellite, and we had the wireline ARPANET, and each was a distinct network. So we isolated the particular communication medium and called it a network. But we don't absolutely have to do it that way, and that's why SDN can sometimes be used to make a much more resilient kind of design. There's also an interesting evolution that came out of the Jet Propulsion Laboratory work starting in 1998. My colleagues and I began thinking about how to do interplanetary communication. And here we have a really serious problem because the speed of light is too slow. And the distance between Earth and Mars is anywhere from 3.5 to 20 minutes one-way propagation at the speed of light. So, and it's a disrupted communication. If you have something on the surface of a planet and the planet's rotating, eventually you can't talk to it because it's rotated, and we haven't figured out how to stop that. So we have to cope with it somehow. So the idea was that we would make use of this notion of tolerance to variable delay and tolerance to disruption. And one of the means by which we did that was to allow the network to store content. Now, in the early days of ARPANET, and certainly most of the history of internet, there hasn't been enough memory available to store things in the routers. Basically, if you didn't have a place to send a packet, you threw it away. In this particular formulation, the idea is that the routers actually have memory in them. They hold on to data until a connection or a link can be made available or recurs, and then you transmit the data. So this is a literally store and forward network, except there's a lot of store in addition to the forward. The other thing we ran into was a little problem with routing. Suppose you're on Mars and you want to send something to a destination on Earth. And suppose you try to use the classic domain name system to do this. So you would do a lookup of a domain name. Well, the server for that is back on Earth somewhere, right? So you do a lookup. It takes an arbitrarily long time to get the answer back. What's the IP address I'm supposed to actually send this thing to? And by the time you get that information, the IP address has changed because the destination was mobile, it was in a different network. So we did late binding instead. We basically say, find the planet first. And after you figure out which planet you're going to, after the packet, or the bundle in this case, gets to the planet, then do the local lookup to figure out where it's supposed to go further. So these things were all designed into the system, and they are yet another example of a kind of software-defined networking. Now, some of you, I'm sure, are aware of this term Internet of Things, and we're seeing this emerge very, very rapidly now with all kinds of appliances and devices showing up in the Internet. Here are just a few of them. I used to tell jokes about things like, Internet-enabled refrigerators and Internet-enabled picture frames. But it's not a joke anymore. These things are actually available. I even used to say that someday every light bulb in the universe will have its own internet address, as if, haha, that would be funny, except somebody just sent me an LED light bulb with an IPv6 radio in it. It costs about $20, and they will probably last for 15 years. The radio only costs about 50 cents. So the idea here that you could have an internet-enabled light bulb is not a joke anymore, and it will probably turn out to be quite useful. Now, all of these devices, and then there's the guy in the middle with the internet-enabled surfboard. I'm sure you've all heard about that. He thought while he was sitting on the water that if he had a laptop in the surfboard, he could be surfing the net while he's waiting for the next wave. So he stuck a Wi-Fi server at the rescue shack on the beach and sells this as a product. So I think that all of these things lead to the conclusion that the software, the flexibility of software-defined networks will allow us to accommodate quite a broad range of things that we don't normally think of as being internet-type devices. Here's another example. I have a sensor net at home, which is based on IPv6. It's a commercial product that was built by a company called Archrock, which was acquired by Cisco Systems a couple of years ago. This is another example of software-defined networking because each of the devices has sensors in it, looking at temperature, humidity, and light levels in each room in the house, and samples that information every 5 minutes and then sends it through an IPv6 dynamically adaptable network. So this network is actually, the devices, the sensors are also store and forward relays, and they're constantly measuring their connectivity and constructing the topology of the network. And even in a residential setting, sometimes the connectivity will change depending on local interference or other kinds of conditions. So this is another example of a very adaptable software-defined network. It's interesting, these little devices are about the size of a mobile. They run on 2 AA batteries and they last for about a year. And it's a very impressive performance. One of my rooms is the wine cellar, and I'm sure many of you have heard stories about the fact that if the wine cellar gets above 60 degrees, I get an SMS on my mobile telling me that the wine is warming up. This has happened a few times when the power has gone out. For a while, I thought that I could do something really clever, that I could figure out if anybody had gone into the wine cellar without my, when I'm away, because I could see whether the lights had been turned on, but I don't know what they did in there. So I had the idea of putting an RFID chip on each bottle in the wine cellar so I could do an instantaneous inventory to see if any bottles have left the wine cellar without my permission. And I actually, this fantasy was actually about to be fulfilled. I had a visit from someone who's building an RFID detector system that has little flat RFID labels that you just hang on the bottles. And as you walk around in the wine cellar waving your RFID detector, eventually it picks up every single thing that's in the cellar. The problem with this, of course, is that if you go into the wine cellar and drink the wine and leave the bottle, I can't tell that that's happened. So now you have to put sensors in the cork, and if you're going to do that, you might as well sample the esters and then interrogate the cork before you open the bottle. And if that's the bottle that got up to 90 degrees someday, that's the one you give to somebody who doesn't know the difference. So, so there's a useful thing to have around the house. The thing that's important, though, is that these kinds of casually deployable networks are the beneficiaries of some of the software-defined networking ideas that I'm sure many of you are pursuing. So I want to emphasize how important this flexibility can be to take advantage of available communications capacity, to take advantage of the dynamics that software-defined networks promise. So I'd like to finish up by drawing your attention to some really tough problems. These are not all solvable by software-defined networks, but you should have these in the back of your mind, because if you're serious about bringing new networking capability to a world that is becoming very, very accustomed to it and very interested in it, these are going to be problems that we need to solve. One of them is accessibility, not only basic accessibility to the network itself, but also as you work up to higher layers of the architecture into the application space, how do I make the applications accessible, especially to people who may need assistance if they have visual impairments or have hearing impairments or have motor impairments. They may need extra attention in order to make the applications useful. Another is to try to keep the internet, or whatever it evolves into thanks to your work, free and open. I can't emphasize how important that has been, because the cornucopia of ideas in the internet have come about because of this other bullet called permissionless innovation. You don't have to ask permission of every ISP in the world in order to build a new application on the internet. You just build it and put it out there and let people use it. So this notion of keeping things open and free is very important, not only for democratic purposes, but also for purely economic purposes, and also for the benefit of humanity sharing information. When the World Wide Web was first released in the early 1990s and became very visible thanks to the Netscape Communications and Mark Andreessen and his team creating the first Mosaic graphical browser, it was astonishing how quickly so much information poured into the net. People were not interested in being remunerated for sharing information, they just wanted to know it was useful for somebody else. Despite all of the monetization that goes on in the internet today, that ethic is still there. People are still sharing information because it is satisfying to know that it was useful to someone else. We should try to preserve that. We also have a problem because the network is, it can be abused, and it is abused. All kinds of things happen, whether it's fraud or bullying or identity theft, or deliberate attempts to penetrate your laptops and turn them into zombies and part of botnets, or sending other malware around. All that stuff is going on, and we want to make it safer for people to use the system, otherwise they won't use it for anything serious. But more important, we also should be promising not only freedom of expression, but freedom from harm. Now, we can't promise or guarantee that, but we can certainly build systems that resist the kinds of attacks that we see happening in the internet today. So as you think your way through what software-defined networking could mean, keep in mind that these are problems that the internet today is experiencing, and that you have an opportunity to think your way through resisting some of those problems by designing and building software-defined networks that can help make the system safer for everyone to use. The other thing which is happening is this huge debate about the management of intellectual property. I can understand why someone who writes novels or writes music or writes songs or creates movies and so on, who's very dependent on monetizing the creation of that work, would be very concerned about the internet and the World Wide Web. You understand the way the World Wide Web works is the browser goes to a destination, copies a file, and then interprets it. So the World Wide Web is a giant copying machine, and that's pretty scary for somebody who's trying to control who copies what. So we have this tension right now between people who create intellectual property and people who use it and consume it. And I think that here again, software-defined networks may turn out to be one of the avenues for dealing with this problem. I don't think that we can absolutely prevent copying. It just isn't going to happen. Once things are in digital form, it's just too easy to copy and distribute. But you may be able to create an environment where access control is recorded and audited in some way to expose abuse can be achieved. And so once again, you may have an avenue for coping with this. We may need some new business models too. People may need to understand that you can't just build your business model around preventing people from copying things, and you may need to think of a different way to deal with it. And finally, just to observe that networking in its current form and what it may evolve into, with thanks to your work, is it changes the economics of communication in a very dramatic way. It used to be that paper was the cheapest way of distributing large amounts of information, and newsprint in particular was very inexpensive. So the newspaper business turned out to be a very, very good business. You know, people wanted to read the news, and as long as they were reading the news, they were exposed to advertising, and the publishing business became a big economic engine. But then along comes digital communication. It's cheaper than paper, and it's more flexible, so people don't have to see the same ads. They can see different ads, which is what has driven the Google model. These kinds of dramatic changes in economics are precisely what causes businesses either to evolve or go under. You remember, Darwin only gives us two choices, either adapt or die. And you know, of the two, I prefer to adapt. I don't know about you. So the point here is that as you explore new networking ideas, keep in mind that they may change important pieces of economics that will change business models. And that some people, maybe you or your company or someone else's company, will have to adapt to the results of your work. I think that's my last slide. Yes, that's it. So thank you. I appreciate the chance to chat. And I'm happy. Guru, I'm happy. I don't know how much time I just took, but I'm happy to do questions.
A couple of questions, not a lot, but we have time for a couple of questions. So please use the microphone if you can. Anyone?
No, I think he's not going to the microphone. He's leaving the room. That must have been. That was really a bad speech. I'm sorry about that. Okay. Well, if there aren't questions, then I do have a little surprise for you. Okay. Oh, there is one. I'm sorry. There you are. Yes.
Hey, Vint, I was wondering, I know you've been thinking a lot about bit rot in terms of documents over hundreds of years. Is there any update on that?
Yes, thank you very much. It's a good question. So here's a really tough problem that is not obviously solvable by software-defined networking. Every single day, you use tools to create complex objects, whether it's a text document or a presentation, or maybe it's a movie file, or maybe you're even a game inventor. You create these very complex objects that can only be usefully perceived if they are interpreted by software. This is true also of web pages, where you need a browser, which is a substantial amount of software to actually render the object. We're now at the point where not all objects that we create can be rendered in the simple way of printing them on paper. So the big concern I have is that over time, the software that will interpret the objects that we invest time and energy in creating won't be available to interpret those objects anymore. Maybe the software will not be moved to the next version of an operating system. Maybe the company goes out of business. Maybe the company changes the version of the software so that it isn't backward compatible with something that you created before. But I want you to think now in long periods of time. Let's imagine it's the year 3000, and you've just done a Google search, and you've turned up a 1997 PowerPoint file. Let's even imagine you're running Windows 3000, just for the sake of argument. So the question is, does Windows 3000 know how to interpret a 1,000-year-old PowerPoint file? And the chances are pretty good that it doesn't, and this is not a gratuitous dig at Microsoft. Even if we were using open source standards, it might not be possible to make those standards implementations 1,000 years from now backward compatible. So the question is, what do we do? And there are several answers. One, we try to standardize representations. We try to find ways of describing the structure of some of these complex objects so that people could reproduce, if necessary, the software to interpret them. Maybe cloud computing will help us. Maybe we can emulate hardware, run the older operating systems that can support the older applications so that we can still interpret older objects, older digital objects, over a long period of time. If we don't do this, then the people of the 22nd century may wonder about us, because so much of us and our daily lives are tied up in digital objects that we've created, whether it's email or other kinds of applications. To give you a very concrete example of the difference between our society and one which was 150 years ago, some of you have probably seen a movie called Lincoln. It was based on a book by Doris Kearns Gooding, and she was able to reconstruct the dialogue of the time by going to about 100 different libraries to find the letters that had been written by the principals to each other talking about the issues of the time during the Civil War. Now, imagine trying to do that 100 years from now, where you would be trying to find the email that people had exchanged to talk about, or the blogs, or the web pages, and so on. And despite the effort that is, the Internet Archive that, help, who's doing that? Brewster Kahle, thank you. I'm not sure that Brewster will succeed in actually recording everything that we would want to find. So if we don't find a way to preserve this information and make it continually renderable, we may actually lose a great deal of history. So thank you for that question. That's a problem that we all need to work on. Okay.
Any other questions?
I don't see anybody. So now you might wonder about that little opening film. We had a lot of fun doing it, but it also turned out we made a few mistakes. So I thought you might get a kick out of the outtakes from the movie. So could we roll the outtakes?
Maybe, yeah.
What is it? Actually, how about this loss estimation update? That on really.
Yeah. Now let's just take a look at this script here. You're out of your mind. You're gonna do what to my office? You guys are crazy.
What happens if you button the jacket? I know it's uncomfortable.
Looks more British. Looks more British.
Stiff upper lip.
James, what the hell are you doing here? Can't you stop hanging around in my office?
Sorry, sir.
Oh, shit. Helicopters bump when they're taking off, you know. And all this for who? The star of the internet, Vint Cerf?